For the output resistance of the first stage, we have to make something different because, now we need to take into account the loading of the second stage. But first, let's draw the small signal model. So at the base, I have R3 and R4. This is base. This is R pi 3 emitter, GM V pi 3 collector, which is grounded. I'm going to put RO3 in here again. RL, V out, R5, RO3. Now, if you take a look at the overall amplifier structure, when you are looking from here, in fact, the output resistance of the second stage appears like a resistance in here. So in that case, you have to take it into account. So there can be a mistake in here, like, you can say that, oh, my Vy is in here, so what should I do is, like, this Vy is shorted and the output resistance is fine like this, which is not true. When you take a look at the overall structure, in fact, your actual signal is in here, you should ground this one. So even if you ground this thing, you may have something in here. So you have to take RR2 as the input resistance when you are looking from the output of the third stage. So your actual circuit should look like this. So you have RR2 in here. In that case, RR is defined in here. All you need to do is using the reflection. So we have R5 in parallel with RO3 in parallel with the resistance seen from here, which is the reflected version of these three resistances, because the current passing through here is I base, the current passing through here is beta plus 1 I base, and therefore we have to write it as like RR3 or overall ROut equal to RO3 R5 in parallel with R pi 3 plus R3 R4 RR2 all in parallel divided by beta plus 1. And of course, in this expression, this part and this part will be dominant. RO3 is quite large compared to the others. So, if you wish, you can ignore RO3 in here to find ROut. So to summarize, for this amplifier, we find the gain of each individual stages. We just multiply them with each other. Rin is Rin1 and ROut is ROut3. But when you are finding this, you have to be careful about the loading. For the voltage gains, loadings are obvious, Rin2 and Rin3. For the output resistance, when you're looking from here, you have to take into account the resistance seen from here as well, because it's going to be reflected in here. For the second stage, it's not that critical because you are looking from the collector edge of Q2. So when you're looking from the collector edge, the resistance at the base may not be that significant, especially when the emitter is grounded. But for a common collector amplifier for the third stage, when you are looking from here, any resistance at the base is reflected and seen as a contribution to the output resistance. On this amplifier also, you can work on this small signal range. As you remember, small signal range for MOSFETs, we said that VGS should be less than 0.2 VGS minus VTN, and for BJT, VBE should be less than 5 millivolts. So when you take a look at this structure, which transistor base emitter or gate to source voltage limits the overall gain? So for matching the small signal, which transistor would you play with? Think about it for a while. So as you see, for M1, source is grounded. Let me use another pen. So source is AC wise grounded. So VGS 1 is in fact equal to Rin divided by Rin plus R signal times V signal. For the second one, again this node is grounded. What you have is VBE2, and I can say that VBE2 is equal to Vx, which is AV1 times V signal. And for the last one, VBE3 is equal to, if you name this node as Vy and this one as Vx, Vy divided by RL plus R5 plus RE3 times RE3. So this should be in parallel combination. So small signal condition should be valid for all of them, which means that this should be less than 5 millivolts, this should be less than 5 millivolts, and this should be less than 5 millivolts. So which stage do you think limits the maximum input signal range? I think the answer is quite obvious, because for the first stage, you don't have any gain until you reach to here. So, I mean, if you assume that Rin is quite large, VGS1 is equal to V signal. So if this condition says that, let's say, VGS should be less than 10 millivolts, then V signal less than 10 millivolts should be good enough to keep this M1 in small signal range. For the second one, input is the amplified version of the V signal. So you have AV1 times V signal, assuming that Rin is much larger than R signal. So if this gain is like, let's say, 10 or 100, whatever it is, let's say it's 10. So to be able to provide this expression, V signal should be less than 0.5 millivolts. So small signal restriction on V signal because of this Q2 is much smaller than the small signal restriction on M1. If you take a look at the third transistor, this was the expression, and be aware of this, like Vy is equal to V signal times AV1 times AV2. It's even a larger value. So now this thing should be less than 5 millivolts. So at each stage, you are multiplying your input with the gain, and providing the small signal restriction for the later stage transistor is getting more and more difficult as the gain increases. So if you are worried about small signal range, you have to take a look at the last transistor for most of the time if the previous stages have large gain. So this Q3 will put the more strict restriction on the V signal voltage. So if you keep this thing in small signal range, it's for sure that this one will be in small signal, this one should be in small signal. So please work on this thing as an exercise and try to find numerical values for this V signal for small signal operation. So as an exercise, calculate maximum amplitude of V signal to keep all the transistors in linear, maybe I should use different wording in here, in small signal range. Okay, please try to solve it by yourself and you will see that the main limitation is coming from the last stage. Most of the time, if you are dealing with multi-stage amplifiers, if every stage puts some gain, most of the time you have to worry about the last stage, last transistor, for keeping all the amplifier in small signal range. So before finishing, I want to discuss one more thing, which is the output voltage swing, which is also an important concept. So let's think about this common source width degeneration amplifier. We always do the small signal analysis, but of course, when you take a look at any node, it has both DC and AC. So for example, think about this node. Let's say this is drain, gate, and source. So you can write the drain voltage as, which has both AC and DC, okay, as some DC voltage, VD, plus VD voltage. Similarly, source has the same thing. Vs is equal to Vs plus V sub S. And of course, because of the isolation capacitor, V out has 0 DC. So because of this isolation capacitor, DC voltage in here is ground. So this thing has no DC. And the same thing for Vg. You can write it like Vg is equal to Vg plus V sub G, both AC and DC. So assume that you apply a sinusoid at the input with some amplitude. And let's assume that we have a gain of AV. At the output, you will see a signal, which is of course with 0 DC level, where the amplitude is given by AV times, let's say, V in, or let's say V in peak to V in peak, let's say. It's going to be multiplied by AV. But when you take a look at this drain voltage, the DC level is VD, and you had the same signal on top of it, which has AV times V in peak. I have a question in here. Assume that you increase the amplitude of the input voltage. Do you think that the amplitude of the drain voltage will follow it, no matter how high input you apply? At some point, you expect some clip off, right? I mean, if you increase the input voltage amplitude too much, after some point, input should be clipped off either from the top or from the bottom, or from both of them. So clipping off occurs at the large amplitudes of the input. So here is a second question. How can you find this clipping off point? If this is VD, what is the distance in here? What is the maximum allowable output signal? Or like in here, what is the maximum allowable output signal in here? So this range is in fact defined as output voltage swing. And to have linear amplifier, of course, you want to make this range as large as possible. Here is a numerical example. Assume that I have 12 volt supply. And let's assume that this VDDC voltage is 8 volts. And in here, let's say we have 4 volts. Again, for numerical values, VTN is given as 1, let's say, and VGS minus VTN, let's say, given as 1 volts as well. So let's try to find the output voltage swing for this amplifier. So when you draw VD, we have 8 volts in here. And of course, when you have the input, you start having amplification. My input is this one, let's say. Please note the 180-degree phase shift between input and output. This is common source with degeneration, so there should be this inverting amplifier, so there should be 180-degree phase shift. So when you have, let's say, 1 millivolt signal, and assume that AV is given as, let's say, 100. These numbers just I'm throwing out from my mind. They may not be realistic, but don't worry about it for the time being. So when you have 1 millivolt and when you have 100 volt per volt gain, the top point will be 8.1. This point will be 7.9. So you keep increasing your input. If you apply 10 millivolts, then you would have like a signal like this one. So this point will be 9. This point will be 7. When do you think that the first clipping off appears at the top point? So when the signal will be clipped off. Any node potential in a given circuit cannot exceed the supply voltage. So this voltage can never exceed 12 volts in here. So the first clip off occurs when you reach, let's say, 12 volt in here, which is the supply. So which is VDD, which is 12 volts. When you reach 12 volts, clipping off occurs. So the maximum voltage peak which is allowable in here is 4 volts. If you divide it by the gain, the maximum signal that is allowed at the input is then 40 millivolts, because my gain is 100. For the bottom part, the limitation comes from here. Remember that this transistor should be always in saturation, which means that VDS should always be larger than VGS minus VTN. So this voltage should always be larger than 1 volt. Okay, so at the bottom part, when you hit this boundary, let's say 5 volts, below this point, transistor is not in set anymore. And because of that, my small signal model is not valid, my small signal gain is not valid, and the amplifier will be distorted. Amplifier output will be distorted. So this is the maximum voltage that you can see without distortion in here. So this range corresponds to, for this particular example, 3 volts. Okay. So output swing is the distance between this point and this point. This is my output swing. But in such a calculation, you should be aware of like you're applying a sinusoid, which means that the upper cycle should have the same amplitude with the lower cycle. So at the upper part, you have a room of 4 volts, but at the bottom part, you have a room of 3 volts. So which means that practically your output voltage swing is the double of the minimum one. Like your output voltage swing is 6 volts. So the V peak to peak can be at most like 6 volts because the lower boundary is 3 volts away from the DC. The upper boundary is 4 volts away from the DC. So let's name them as like V positive max is 4 volts. So this is like V negative max is 3 volts. So generally, you say that output voltage swing is 2 times minimum of V positive max and V negative max. So your output voltage swing is like 6 volts in this case. From here, you can find the maximum allowable input signal. What you need to do is you just divide this 6 volts by the gain of the amplifier. So in this case, at the input, 60 millivolt peak-to-peak signal is allowed for linear operation. Okay, this is the maximum input voltage allowed in the allowable output voltage swing. So two things which is limiting your output voltage swing. One is the supply voltage. None of the node voltages in a given circuit, unless you have some like capacitive components, charging elements or whatever, cannot exceed the supply voltage. So this node cannot be larger than 12 volts. So that puts the first limitation. For the bottom part, you have to keep the transistor in saturation for amplifier operation, of course. In that case, VDS is given as like with this VGS minus VTN expression. Since this node DC voltage is fixed, the AC voltage in here can go like this. Here you may think that like you can say that okay, there is some AC voltage on top of the source voltage, so why don't we take it into account? But please note that the gain from here to here is much smaller. The gain from here to here. If this is like 100 volt per volt, the gain from here to here is like less than 1 volt per volt, because in that case the amplifier is operating like a common collector amplifier. So the signal in here, the signal on top of this 4 volt is negligible compared to the signal at the drain point.